Hi everyone, and thank you for attending the Meta Learning and Core-Set competition workshop. I am Adrian, and I'm going to present the featured MetaDL competition. Later today, you will be able to attend 2 oral sessions presenting the first and second best solution of this challenge. Thank you to all of our collaborators for this project. You can find the complete list on the workshop website if you are interested. We also want to thank our challenge sponsors. Challenge is the challenge organization coordinator and also provided prize money. Microsoft provided cloud computing units through the Azure platform. So let's define some background to explain what is the MetaDL challenge and where it lies in the meta-learning challenges ecosystem. There exist many competitions on different meta-learning subfields. For example, in performance prediction, where a system needs to choose an algorithm based on its performance on other tasks. The ChalLearn gesture recognition challenge in 2011 that focused on one-shot learning with videos. The AutoDL challenge series, which goal was to create a fully autonomous system capable of tackling different modalities. And probably the one that resembled the most MetaDL, the few-shot humpback whale identification competition, which was hosted on Kaggle 2 years ago. And it was similar to MetaDL because you only have access to a few examples per class in the problem of image classification. Like in the AutoDL challenge series, we want to create a series of meta-learning competitions. For the AutoDL challenge, only a few participants did use meta-learning approaches, and we wanted to specifically orient this new challenge toward this kind of solutions. We focused on one specific modality, images, and a problem that typically needs some kind of meta-learning. We considered few-shot learning image classification, also because of its potential applications in domains that are known to have very little label data, such as medical image analysis. And also, image classification has a lower barrier to entry than other meta-learning subfields. So here, we present a quick overview of the few-shot learning for image classification setting. Let's first compare the few-shot learning and standard machine learning settings. And let's consider a small training set with only a few examples per class associated to a test set with potentially much more examples. These two sets would define a dataset. In the few-shot learning framework, we define a metadata set as a collection of such datasets. Then we could define the meta-train dataset to be the collection of datasets used during meta-training phase of a meta-learner. And similarly, we could define the meta-test dataset to evaluate the meta-learner performance. In order to create these sub-datasets, and thus the metadataset itself, one would have to sample classes from a pool. We used the work of the metadataset paper from Triantafilou et al. For the data generation process. So we defined these two class pools from which we would generate data during each phase. At meta-test time, the data is in the form of episodes that we've previously defined. However, at meta-train time, the data can have different forms. It can be episodic or have a more traditional approach that we call batch mode, where we consider all meta-train classes at the same time. Now, what are the goals of the MetaDL competition? First, many few-shot approaches take time to meta-train, and we want to evaluate procedures under a computational constraint. Then we would be able to benchmark reference methods against approaches developed during the competition under this constraint. And finally, we want to put an emphasis on automated solutions. As in the AutoDL challenge series, we would want a system that is able to adapt its meta-learning procedure based on the data at hand. Now, let's dive into the challenge design and our setting choices. So the challenge is decomposed in 3 phases for participants. In each of these phases, the participant is exposed to a specific metadata set. The first phase is the public one. Participants are able to do local experiments with Omniglot, a popular dataset in the few-shot learning literature. The second phase is the feedback phase, and participants' submissions performance constitute the competition leaderboard. The dataset used here is Sci-Fi 100 with a particular class split and is hidden to participants during the competition. The final phase is used to create the final rankings. The few-shot learners are blind tested on a new private metadata set. Models are meta-trained from scratch here. For this competition, we designed an API to better encapsulate the different learning stages of a meta-learner. Using this API, one has the choice of incoming data configuration. As we've previously mentioned, the data can come in the form of episodes, which are essentially small datasets, or in the form of batch of examples, which could be compared as having a unique train set containing all classes from the meta-training class pools and their associated examples. Also, one important aspect of our setting is the time constraint that we enforce. We allow the meta-training phase to last for 2 hours maximum before being evaluated on meta-test episodes. The metric we use to evaluate few-shot learners' performance is the simple accuracy of the 600 meta-test episodes. This type of evaluation procedure is common in the few-shot learning literature, and it is used both in the feedback and final phase here. One important aspect of evaluation is the type of methods our experimental setting favors. Blind testing is the part where we take algorithm from the feedback phase to be meta-trained from scratch and evaluated on the final metadata set. It allows to evaluate the ability of meta-learners to adapt to tasks from different distributions. We run the challenge on the Codalab platform, which is an open source project of which we are community lead. Codalab is free for use for all. To run the calculations, we use a generous donation of Microsoft of 100,000 cloud units. We prepared a Docker including many machine learning toolkits and scientific programming utilities such as TensorFlow, PyTorch, and scikit-learn. We ran the jobs of the participants in virtual machines equipped with 4 NVIDIA Tesla M60 GPUs. One VM was entirely dedicated to the job of one participant during its execution. We created a starting kit in order to bootstrap participation for the competition. In this starting kit, we implemented very popular baseline methods for few-shot image classification. And the first one is the MAML algorithm, and more specifically, its first-order approximation. MAML is a bi-level optimization procedure. Then we implemented the prototypical networks, which is a method that aims to learn a specific metric space. And it is also known to be less expensive, computationally speaking, than other methods. And finally, we implemented the transfer baseline, which basically take pre-trained networks, fine-tune them with meta-trained data, and evaluate the performance with meta-test episodes. You can find references about these methods and also the data generation process we used in the next slide. During the competition, 78 participants registered and 13 participants were eligible to enter the final phase. Here are the top 3 teams. In the first position, we have the meta-learners team, which developed an ensemble of 4 meta-learners with a time resource manager. They will do an oral presentation about their solutions later today. Then we have the SETOM team, which developed an optimal transport-based method that was heavily inspired by the recent work of Yu-King Hu. And finally, we have the Edinburgh team, which developed a method which is a mix of QDA, quadratic discriminative analysis, and protocol networks. All code is available on the competition website and are open source. And also, if you are interested in the whole presentation, please double check the time of these presentations on the workshop website. We present the submission survey that participants had to fill out after the competition. More specifically, 2 insights about it. First, the choice of using pre-trained neural networks. The majority of participants did not use pre-trained neural networks. Those who used it tend to rank higher. But the second best team did not use this technique and nearly perform as well as the first submission, suggesting that other approaches could be considered to bootstrap a neural network's performance. We also asked about the input data stream choice. This question is still considered in the literature, even though it is believed that episodic mode tends to be better in few-shot learning, because it makes the meta-train and meta-test settings match. The large majority of participants did use the episodic mode. More information about these details and other questions will be available on a dedicated post-challenge analysis paper to be submitted to the AAAI journal under the competition track. As we mentioned, this challenge is the first of a series. We are interested in developing other challenges using other domains, as it was the case for the AutoDL challenge series. We are also investigating the possibility and potential impact a competition could have on other tasks, such as in reinforcement learning or few-shot image segmentation. If you want to be informed about these future challenges, sign up on the competition series website, which is also the workshop website. And if you have any suggestions about potential challenges or interesting approaches we could tackle, please feel free to join the dedicated Google group. Thank you.